we were learning about reference angles and how to use reference angles to calculate the exact value of the cosine function and sine function for angles that are multiples of pi over 6 radians and pi over 4 radians, which is also 30 degrees and 45 degrees. So we had worked everything on this page except for the very last problem, the sine of 225 degrees. What's the exact value of the sine of 225 degrees? Well, here's my unit circle. And the angle 225 degrees is less than 270, but more than 180. So here's the terminal, or here's the initial side, standard position. And so 225 is more than 180, but less than 270. So that's the angle 225 degrees. Well, 1/2 revolution is 180. Right? This is the acute angle between the terminal side and the negative x-axis. If 1/2 revolution is 180, what's this acute angle between the negative x-axis and the terminal side? 45 degrees. So 45 degrees is the reference angle. And is sine positive or negative in quadrant 3? Negative. So the sine of 225 degrees is going to be the negative of the sine of 45 degrees. And remember, when we put a minus sign out front of the sine function, right, that's -1 times the sine of 45 degrees. And you know from the previous page, the sine of 45 degrees is equal to square root of 2 over 2. So this is minus the square root of 2 over 2. Okay. So we're using what we know from the previous page. Right? We know the exact value of the cosine function, sine function for 0 degrees, 30 degrees, 45 degrees, 60 degrees, and 90 degrees. And we're just using reference angles and symmetry and things of that nature to evaluate sine and cosine at different angles. Okay? All right. So if you flip over the page, top of page 6, we're instructed to find all values of t in the interval from 0 to 2 pi that satisfy the given equation. So the first equation in A is we got to find all the angles t in radians such that the sine of t is equal to square root of 2 over 2. Well, we know from the previous page, from previous work, that for for the angle pi over 4 radians, both the cosine function, right, the cosine of pi over 4 and the sine of pi over 4 both equal square root of 2 over 2, right, from the previous, from page 4, I think it is. Yeah, bottom of page 4, okay? So one solution to this equation, right? We know that the sine of pi over 4 is equal to square root of 2 over 2. So one solution to this equation is t equals pi over 4. Okay? That's one angle between 0 and 2 pi, that the sine of that angle is equal to square root of 2 over 2. Now the question is, what is the other angle? Well, this is where we're going to use symmetry. A circle with its center at the origin has all three forms of symmetry, doesn't it? It has y-axis symmetry, x-axis symmetry, and it has origin symmetry. So we take this point and we go directly across. We find a point that is symmetric to it on the left side of the y-axis. That point that is symmetric to this point has coordinates minus square root of 2 over 2 square root of 2 over 2. Remember, if a graph has y-axis symmetry, for every point xy on the graph, the point minus xy is also on the graph, okay, for y-axis symmetry. So we just got to change the coordinate, right, the sign of the x coordinate to get this point over here that's symmetric to this point. So I draw the terminal side through that point. Question is, what's that angle that has the terminal side going through that point? The sine of that angle, right? Remember, sine is equal to the y coordinate. The sine of that angle will equal square root of 2 over 2. Well, because of the symmetry, this reference angle here with this terminal side is equal to pi over 4 radians as well, just like it is over here, because of symmetry. Well, we know 1/2 revolution is equal to pi, okay? From the positive x-axis to the negative x-axis, that's 1/2 revolution. That's equal to pi radians. So if I subtract pi over 4 from pi radians, I get this angle from the positive x-axis to this terminal side. So pi minus pi over 4 is equal to 3 pi over 4. So this angle that has this terminal side going through this point, that's symmetric to this point, is the angle 3 pi over 4.
Can you explain that again?
Okay, which part? This point is symmetric to this point across the y-axis.
Okay.
The terminal side of an angle goes through that point. Okay, this is the terminal side that goes through that point. The reference angle for this angle is also pi over 4 because of symmetry. Okay, the reference angle, right, then you had the angle pi over 4 over here. The reference angle for 3 pi over 4 is the angle pi over 4 because of symmetry. And so this angle between the initial side and the terminal side here has to be 3 pi over 4 radians, because 1/2 revolution is pi radians. And when we subtract the reference angle pi over 4 radians, we get the angle 3 pi over 4 radians. 3 pi over 4 radians plus pi over 4 radians equals 1/2 revolution, pi radians.
But that's not one of the values, correct?
Say what?
That's not one of the values, correct? Like, that's not one of the values of t, right?
Well, t in this case will equal 3 pi over 4.
Okay.
Okay? Because the terminal side of the angle 3 pi over 4 goes through this point, and the y coordinate for this point is square root of 2 over 2. Okay. So the sine of 3 pi over 4 is equal to square root of 2 over 2. So those are the two angles between 0 and 2 pi where the sine of each of those angles is equal to square root of 2 over 2. So the solution to this problem is t equals pi over 4 and t equals 3 pi over 4. We knew sine pi over 4 equals square root of 2 over 2 from the bottom of page 4. So I had to use a reference angle to find the second solution, 3 pi over 4. Yeah. Due to symmetry across the y-axis, we knew there were two angles where the sine of those angles, right? The sine of those angles is equal to square root of 2 over 2. Any other questions? All right, so let's look at B. We have the cosine of t is equal to minus the square root of 3 over 2. So there are two angles between 0 and 2 pi where the cosine of those angles is equal to minus square root of 3 over 2. Well, here's my unit circle. And what we know from the bottom of page 4 is that here's the angle pi over 6. And the terminal side of the angle pi over 6 passes through the point square root of 3 over 2, comma 1/2. We know that the cosine of pi over 6 is equal to square root of 3 over 2, right? Well, here we're looking for the two angles where the cosine of those angles equals minus square root of 3 over 2. So again, we're going to use symmetry. The point, remember, cosine is negative in quadrant 2 and quadrant 3. So the point directly across the y-axis from this point, right, is symmetric to that point. And it has coordinates minus square root of 3 over 2, comma 1/2. So if I draw the terminal side of an angle through that point, right, here's that angle. And the cosine of that angle is equal to the x-coordinate minus square root of 3 over 2. So if we can figure out what that angle is, it's one solution to our equation up here. Well, because of symmetry, the reference angle for this angle here has to be pi over 6 radians. And we know 1/2 revolution is equal to pi radians. So pi minus pi over 6 radians has to be the value of this angle from the initial side to this terminal side. So pi minus pi over 6 is equal to 5 pi over 6. So this angle right here is 5 pi over 6 radians. 5 pi over 6 plus pi over 6 equals pi, 1/2 revolution. So one solution to our equation up here, okay, so that means the cosine of 5 pi over 6 is equal to minus square root of 3 over 2. So that's one value of t, right? It makes the left-hand side, right? 5 pi, put in 5 pi over 6 in for t, the cosine of that angle is equal to minus square root of 3 over 2. So that's one solution. So let me redraw my unit circle. With the first solution that we know. Here's the angle 5 pi over 6. And here's the point on the unit circle that the terminal side goes through, minus square root of 3 over 2, comma 1/2. Remember, this is the reference angle pi over 6. Well, not only does the unit circle have y-axis symmetry, it has x-axis symmetry. So there is a point below the x-axis on the unit circle that's symmetric to this point, and it has the same x-coordinate as this point up here, minus square root of 3 over 2. Except the y-coordinate is now minus 1/2, not plus 1/2. So if I draw the terminal side of an angle to that point, question is, what's that angle that has its terminal side going through that point? The cosine of that angle is equal to minus square root of 3 over 2. Well, we can figure out what that is because of symmetry. This reference angle between the negative x-axis and this terminal side also has to be pi over 6 radians, just like it is up here. And so what's this angle? 1/2 revolution is pi, and then we add pi over 6, and we get the value of this angle, the size of this angle in radians. So pi plus pi over 6 radians equals 7 pi over 6 radians. So this angle from the initial side to this terminal side down here is 7 pi over 6 radians. And the cosine of that angle is equal to the x-coordinate minus square root of 3 over 2. So now we have our two angles that satisfy this equation. One is t is equal to 5 pi over 6. The other is t equals 7 pi over 6. And we're done. Does that make sense? What we did? Taking advantage of symmetry and reference angles. Okay? That's what we're doing. Taking advantage of symmetry and reference angles. Alright. In the last example, you're given if sine of angle t is equal to minus 2/3 and the point P is in the third quadrant, find the value of cosine t. Ramez, I handed back the quiz, so stick around. After class, I'll give it to you. Okay? All right. So you're given that the sine of angle t, whatever it is equal to minus 2/3, and the point P is in the third quadrant. So here's my unit circle. And the point P, right, is in the third quadrant, right? This is down here. That is part of the circle. So minus 2/3 is really close to -1. So the point must be down here closer to the y-axis than the x-axis. So here's the initial side. Here's the terminal side. This is some angle t. And the terminal side, right, goes, right, this is the point P. And the y-coordinate, because you know sine t is equal to y, right, the y-coordinate. So the y-coordinate we know is minus 2/3. The x-coordinate, right, cosine of the angle t is equal to the x-coordinate. Right? Was the x-coordinate cosine t, are they positive or negative? Negative, right? In quadrant 3, right, they're both negative. Well, there's no point, right, there's no special angle that has a sine value of minus 2/3. How are we going to find cosine t? Well, if you go all the way back, the page, bottom of page 1 of your note packet, we noted that cosine t squared plus sine t squared is equal to 1 for any value of t. Okay? And we write it, typically write it as cosine squared t plus sine squared t, right? When you put the 2 as a superscript on the cosine sign, it means you're squaring it. Okay? Well, we know what the value of sine t is, don't we? So we replace sine t with minus 2/3, and then we solve for cosine t. Okay? And we know cosine t will be negative. So cosine t squared plus sine t squared is equal to 1 for any number put in for t. Well, sine t is equal to minus 2/3. So we just replace sine t with minus 2/3. And now we can solve for cosine t just like you solve for x. Okay. Well, minus 2/3 squared is equal to 4/9. And now we subtract 4/9 from both sides. We have cosine t squared is equal to 1 minus 4/9. And 1 minus 4/9 is equal to 5/9. And now what does squaring? Square root. But cosine t is negative in the third quadrant. So on the right hand side, it's just going to be the negative of the square root of 5/9. Because cosine t is negative in quadrant 3. And so on the left, we have cosine t is equal to properties of radicals. I take the square root of the numerator over the square root of the denominator. Square root of the numerator is square root of 5. Square root of 9 and the denominator is 3. So cosine of the angle t, whatever it is equal to minus square root of 5 over 3. Any questions on that? So now you have everything you need to successfully complete the MyMath or the WebAssign homework. All right. Last week I wasn't going to hand out what is called the unit circle with all the values of the sine function and cosine function for angles between 0 and 360 degrees that are multiples of 30 degrees and 45 degrees. But I changed my mind. So if you already have one of these, don't want one of these, raise your hand when I get it. You don't need one? Kelly? Yeah. All right. So what this front page does for you is, right, all the angles from 0 to 360 degrees are drawn, right? All the angles that are multiple of 30 and 45 degrees from 0 to 360. And so what's in the first quadrant is the numbers that are at the bottom of page 4 of your notes. So how you read this is the cosine of 30 degrees is equal to square root of 3 over 2, right? Because remember, the first coordinate of the point is the x coordinate. And the second coordinate of the point is the y coordinate. And cosine of the angle t is equal to the x coordinate. And sine of the angle t is equal to the y coordinate. So this tells you, without having to use reference angles and symmetry, what the cosine and the sine of each of these angles is, right, between 0 degrees and 360 degrees. Okay? Now we've calculated the cosine and sine for some of these angles in quadrants 2, 3, and 4 using reference angles. But some people like to memorize this so they don't have to keep computing the value of cosine and sine for the same angles over and over again. On the back side, right, is the same information as on the previous page, except it's in table form. So in the first column, right, we have all the angles from 0 to 2 pi in radian measure, and then their corresponding value of cosine and sine. And on the third page, we have all the angles from 0 to 360 degrees, okay, and their corresponding value of cosine and sine. So all that information in the table is the same information that's on the first page, right, on the circle. It's just in table form, okay? And so you might find doing the homework a little easier if you reference this handout, okay? But when it comes exam time, it's got to be up here. Okay? All right. So any questions on that? All right. So what we're going to do next, we're just going to spend a couple of minutes talking about graphs of the sine and cosine functions. All right, give you an introduction to them. Kelly, you need one? Oh, I forgot about you. Sorry, Emma. All right. So now that we know the value of sine and cosine, for certain angles, we can graph functions involving them. So first thing we're going to learn about is the basic graph of the sine function and cosine function. Okay? So in the first graph, we're graphing the equation y equals the sine of x. Okay? Now x and y, when we were learning about the definition of sine, the sine function and the cosine function, x and y were the coordinates of points on the unit circle, right? And x and y satisfy the equation of a circle. X squared plus y squared equals 1. That's not the case in the graph, right? X and y, their context has changed. You know, if we graph y equals x squared, x is the independent variable, and y is the dependent variable. And that's kind of what's going on here, okay? X and Y are not points on the unit circle. They do not satisfy x squared plus y squared equals 1, okay? So in the equation, x is the input variable, which is an angle in radians, and y is the output variable, which is also called the dependent variable. So when you graph an equation, you know what the basic idea is in graphing an equation. You got to select some values of x, and then you got to calculate the corresponding values of y, right? The values of x are x coordinates, values of y are y coordinates. And then you use those values of x and y to form ordered pairs, and you plot those points, and then you connect the dots, right? So I use the angles, what are called quadrantal angles, which are multiple of 90 degrees or pi/2 radians. And since we have to graph in radians, right, I use 0, pi/2, pi, 3 pi/2, and 2 pi. And the reason I stopped at 2 pi initially is the sine and cosine function have a period of 2 pi radians. So this is 0 radians is equivalent to 0 degrees. Pi/2 radians is equivalent to 90 degrees. Pi radians equivalent to 180 degrees. 3 pi/2 radians equivalent to 270 degrees. And then 2 pi radians is equivalent to 360 degrees. And so from the previous section, bottom of page 4, we're using the unit circle. We know the sine of 0 is 0. The sine of pi/2 is 1. The sine of pi is 0. The sine of 3 pi/2 is -1. And then the sine of 2 pi is 0 again. 0 and 2 pi radians are coterminal angles. 0 degrees and 360 degrees are coterminal angles. And then you form the ordered pairs. You have the ordered pair of 0, 0, pi/2, 1, pi 0, 3 pi/2, -1, and 2 pi 0. And then you plot those points. So on your graph, right, here's x in radians. And then we got y, which is equal to sine x. So here is the point 0, 0, right? It's the origin. And then here's pi/2, right? X equals pi/2, and then y equals 1 is up here. So this is the point pi/2, 1. And then we have the point pi 0, which is right here. Then we have the point 3 pi/2 -1, which is down here. And then we have the point 2 pi 0, which is here. Okay? So those are the 5 points from my table, okay? And then, right, you draw a smooth curve through those. Because the sine function and the cosine function have a period of 2 pi radians, or 360 degrees, which means they repeat their values every 2 pi radians, or 360 degrees. So This is one period of the graph of the sine function from 0 to 2 pi. And whenever you graph something for a length of one period, it's called a cycle. So down here where it says one cycle, you can, that's equivalent to one period. Okay? And so because the sine function repeats its values every 2 pi radians, we can graph the sine function from 2 pi to 4 pi by copying this part of the graph from 0 to 2 pi. You notice from 2 pi to 4 pi, the graph looks exactly the same as it does from 0 to 2 pi. That's due to periodicity. And you'll notice that from minus 2 pi to 0 radians, right, the graph looks exactly the same as it does from 0 to 2 pi. That again is due to periodicity. So in graphing the sine function, we only have to graph it for one period, and then we just replicate what the graph looks like for that period, going out to the right and going out to the left. And we get the graph for all values of x, for all angles x. So the domain of the sine function is all real numbers, minus infinity to plus infinity. The range, which is the y coordinates, you can see the minimum y coordinate is -1. The maximum y coordinate is +1, so the range goes from -1 to 1. The x-intercepts in the graph of the sine function, if you look closely, they're integer multiples of the number pi. Right? -2 pi, -1 pi, 0, 1 pi, 2 pi, 3 pi, 4 pi. And so this is, the x-intercepts just turn out to be integer multiples of the number pi. The y-intercept, where it crosses the y-axis, is at the origin. And as I pointed out, the period is 2 pi radians. Right? The graph repeats itself every 2 pi radians. In symmetry, the graph has origin symmetry. So remember, if it has origin symmetry, you can turn the graph upside down and it looks exactly the same, which is the case here. So that is the graph of the sine function. Okay? And so when you come back from Thanksgiving, right, we will look at the graph of the cosine function, and then we'll look at transformations of the graphs of the sine function and cosine function. Okay. So have a good Thanksgiving. All right, Ramez, chart quiz.
I was gonna do that.